So, good morning, ladies and gentlemen, also from my side. My name is Lars Grün, and I have the pleasure to introduce this morning's plenary speaker, Professor Moritz Diehl from University of Freiburg. Professor Diehl studied mathematics and physics in Heidelberg and Cambridge, and he did his PhD at the Heidelberg Interdisciplinary Center for Scientific Computing in 2001. From 2006 to 2013, he was in Belgium, in Leuven, and he was there principal investigator at Leuven's Optimization in Engineering Center, that's UPTEC, and he's actually still affiliated to Leuven, although 2 years ago, he moved to Freiburg, and where he's now a full professor and head of the Systems Control and Optimization Laboratory. Moritz's research interests span from applications to numerical methods, is centered in optimization and control, and the application areas range from chemical engineering, process control, mechatronics, and renewable energy systems. And the latter is also the area where he, some years ago, received a prestigious ERC grant, and it's also the topic of his today's lecture. And I'm particularly pleased that Moritz is going to deliver this lecture because you will see that he's always very enthusiastic about his topic, and he will probably explain to you why this is an important topic to discuss nonlinear optimal control for airborne wind energy systems. So please, Moritz.
So I hope to convince you during this talk that this is an exciting area to work in this community. Let me start by motivating the topic a bit. So, as you all know, in 2022, that means 7 years, when our bachelor students are actually our PhD students, there is no nuclear power left in Germany. That's a decision. Already now half the power plants are switched off. And one of the last ones is Neckar-Westheim, that you see here on this picture. On the other hand, let's take a bit more European perspective. If you look at how Europe gets its electricity, we have 80% either nuclear or fossil fuels. And the rest is a bit of hydro and a bit of solar and wind. So would we need to get back? That's happening at the moment. A lot of people consider starting, or actually it happens that coal plants get fired up again. And that's definitely not what we want. If you look at the last 500,000 years and make a diagram of the CO2 concentration and the surface temperatures, you see they are quite correlated. If you look at the last few 50 years, humanity contributed a lot of CO2 to the atmosphere, and it's definitely contributing to global warming. Here's the ice caps melting since 20 years. So there is, I don't need to convince you, I just wanted to recall these facts to bring this all into perspective. So let's look at, I like it to look at the personal perspective. So what is our personal energy consumption? And there is a wonderful book by David McKay, 2009, which takes this personal perspective, and if you sum up different energy sources, which is not legitimate, but which you can do to get an order of magnitude, we would say that our personal consumption is actually 5 kilowatt. 5 kilowatt is what each of us, while we are sitting here, basically consumes averaged over our lives in a European society, taking all energy needs into account. There's only a bit of it is electricity, then there's transport and heating. It means about 120 kilowatt, no, not about, exactly 120 kilowatt hours per day. It's just a different way to say the same fact, but I like the 5 kilowatt more. Or you could say 12 liters of petrol that we burn every day. I was discussing with Lars yesterday what this conference would cost in petrol. So personally, each of us burns about 120 liters of kerosene for a flight from Berlin to Lecce. I mean, those that came from Germany, which corresponds to roughly 10 days of our average consumption. So one perspective or one way to visualize these 5 kilowatt, which I like, is you think of a large electric heater, these things that you find at some stations in Belgium that you see here on the right. You switch it on when you are born, and when you are dying, it's switched off. That's basically what is our average consumption. It's quite a lot, and we can probably not reduce it by far. So in order to cover these needs with sustainable energy sources, there are basically two that are able to deliver enough for humanity's needs, and these are solar and wind energy. It all comes from the sun. As we know, 1.3 kilowatt per square meter is radiated by the sun, and a part of this drives the wind. But if you average this over the days and the years, solar ground irradiation in a sunny place, okay, since today we know it's not always sunny, but an average, Lecce is better than Germany, and we have about 200 watts per square meter as an average solar insolation. If you harvest this with photovoltaic cells, there are some statistics, beautiful, documented. So we have about 40 watt per square meter. So it doesn't sound a lot. On the other hand, the really exciting number I like, each of us would just need 125 square meters of ground here in Lecce, of solar cells actually, to get all these 5 kilowatt of electricity, which is like the most valuable source of energy. So it would be solving all our needs if each of us would just have 125 square meters of solar cells. It's not excessive, it's maybe an area, 12 times 10, maybe like this stage here. The disadvantages of solar and wind energy are, of course, that they are thinly distributed, so the concentration is the real issue, and the other thing is they are not available at all times. I will not talk about this distribution over time question, but about the concentration, because that's crucial to airborne wind energy. So despite these disadvantages, if you look at the world, and this is incredible statistics. It started actually in Europe, and Germany and Italy were for some time leading the field of solar energy. Now China and the US are taking over, but it's growing strongly, both wind and solar energy in the world. They're getting cheaper and more competitive every day. And if you look at the total installed capacity, we are at these numbers, nearly 500 gigawatt already. And if you divide that by a factor of 5, you get the average production of these plants. And you can already state nowadays, every year we replace basically the electricity production by 100 nuclear power plants worldwide with solar and wind together. So it's definitely not something marginal at the boundary of our society, but it will probably change how we cover our energy needs. So very often these come in 5 megawatt plants, and I looked it up in the internet. There is a solar power plant of 5 megawatt here in Lecce. I forgot the name, but here's a picture I found on the web on a sunny day. And for 5 megawatt, you would need above an area of 100 times 200 meters. In the north of Germany, in climates where the weather is always like today, or very often like today, like Belgium, my home country for many years, we have a coast, the North Sea, and you can install wonderful wind turbines there. And to get these 5 megawatt, you would have a turbine of 150 meters total height, which has a smaller area on the ground, but of course it's still a gigantic construction. And if you look at such a turbine, which is what I'm interested in, the turbine and the tower, they weigh 700 tons. And then you have the foundation. So there's quite some mass involved and a lot of engineering challenges, as you all know. And many of you, I think, are aware of the structural challenges of wind turbines. So this is where we start. And the question that we want to answer is if we could harvest wind power in high altitudes with less material. And that's the motivation for airborne wind energy. And I want to give a motivational video. So of course there are limits due to the structural loads that are acting on a wind turbine. On the other hand, if you look at how it harvests wind energy, it's actually the wingtips which are by far the most efficient in extracting power from the wind field. They move fast and they cover a very large area, so they have very strong aerodynamic effects on the wind field. And the question is, if we could construct a wind turbine which takes everything away that makes problems, like the tower and the inner parts of the blades, and just have these wingtips, and replace them by something that might resemble more airplanes rather than a wind turbine, and connect it with tethers in order to transmit the force to the wind field, which we need to do in order to be able to harvest wind power. So that is the motivation behind our technology. In the lecture, I decided to structure as follows. I first want to talk about how we model airborne wind energy systems and give a bit of an overview of what is the physics behind it. In the second part, I want to talk about the optimal control methods, the numerical methods that we use in order to solve interesting problems in airborne wind energy. And at the end, bring the two things together for the topic of the talk, which is nonlinear optimal control of airborne wind energy systems. And I illustrated at hand of 3 of the companies working in this field. Before I continue, I want to check that the sound is working well. So with my limited motion that I now have, can you hear me at the end? Okay, good. So I stay like this. I think there's nothing much I can do. So the first concept I really want to share with you is what we call crosswind kite power. So the reason why these things are efficient and why the wingtips of a wind turbine are efficient is because they move very fast orthogonal to the wind. So we fly fast loops in a crosswind direction also with these devices, and we will have a very strong force on the tether. That's not avoidable, and it's actually exactly the way how we harvest wind energy. But that's just a force. So the question is, how could we harvest energy, and where would we place a generator? And there are 2 ways to do this, and the first variant is an onboard generator. That's quite trivial if you think of it, and it sounds like a bad idea. You attach small wind turbines to the kite. They have some losses, of course, and then you have the cable that transmits power. What turns out to sound like crazy, namely to put the generators on board, think of the heavy nacelles of a wind turbine. It's not as bad as it sounds, because these generators turn extremely fast, so they can be lightweight for very high amounts of power. And also, what is nice about this is that the propeller can be used to start and land. On the other hand, the real disadvantage is that the cable gets thicker, and you need to transmit high voltage power here. And the generator and the power electronics add, of course, a bit of weight, which seems to double the weight of a wing, according to the industrial partners working on this. Yeah, I want to just show a picture I didn't show in a talk yet, but it's my own addiction to airborne wind energy goes back 23 years, or at least. It was a childhood dream, and here's one of my artistic visions from 23 years ago, where I actually designed these onboard turbines, and I deliberately left out the generator because I thought a generator that could digest this type of this amount of energy that I assessed would not exist yet. So, of course, I always took this as a dream and not serious, because the generators would be too heavy. But there's a different way, and personally I discovered it much later. That is the variant 2, which is doing somehow magically, it's transmitting the power in a very different way, which in a very much more elegant way, I find. So we place the generator on the ground. We fly the kite fast as before, so we have this high force, but then we use this high force to unwind a cable and drive a generator which is placed at the ground. So you can unroll the cable, generate power, and all the power electronics is at the ground now. So of course this will not go indefinitely. We will have a retraction phase. In this retraction phase, we will slow down the kite, we will reduce the force, and then we will pull back the line and consume a little bit of power. The advantage, as I said, is that all the electric high voltage electronics are on the ground, but the disadvantage is that the generator is relatively heavier for the same power because it's turning slower, so you need big gears. So, of course, why this is interesting for numerical mathematicians, it's also that this variant leads to particularly beautiful nonlinear optimal control problems. So think of this process of flying circles and then flying back. That's a very nonlinear and interesting cycle to look at. So my personal discovery of this process was 10 years ago. I really remember the night where I was so excited about this. And afterwards tried to find out if something existed, and also talked with patent lawyers and so on. And at the end you find out that all good ideas exist somewhere, and there was actually an article already from 1980 which did do all the calculations that many of the people now working in this field have done independently like me before. And this article goes back to an American engineer called Miles Lloyd. And he derived a formula which, as I said, everyone in this field probably derived at some point and got excited about it, which I state here in the red triangle, in the red rectangle. So Miles Lloyd still is alive in California. And this formula states that the power that you can get out of a given wing area of an airplane wing, basically, is proportional to the cube of the wind speed, like in all energy extracting devices, wind energy extracting devices, and also to the product of CL and CL over CD squared. And CL is the lift coefficient and CD the drag coefficient. And their quotient is called the gliding number, and it's a very important efficiency measure for airplanes and for wings in general. And so now if you plug into this formula, which is an upper bound, of course, but you plug in a typical weight at a wind speed at 100 or 200 meters of altitude, and the L over D, this lift over drag ratio of 15, which is a very low estimate for inefficient planes, so to say, you get out that you would harvest 40 kilowatt per square meter wing surface. And this is the same for both variants. So that's quite an exciting number, 40 kilowatt per square meter wing area. I will illustrate that number a bit further later. But before, because we have such a, I think, smart engineering and mathematics audience, I will want to try to derive this formula in public on 2 slides so that you get the idea of what is behind this formula. So there are 2 parts of it, and I will derive it actually only for the pumping mode. So if you look at the first question, one might want to answer is which roll-out speed is optimal. And so when we roll out this the cable, the power that we generate at the ground is, of course, the product of the tension in the cable times the speed of our roll-out speed. The tension is, of course, getting smaller when we roll out faster because the kite sees relatively less wind. And when we roll out as fast as the wind, which you see here on the lower right side, then we don't have any tension left. And it turns out that the dependency on this difference speed is actually quadratic, so we get this tension curve here. And, of course, the roll-out speed is this linear curve. When you multiply them, you get this yellow curve, and the maximum is at 1/3. So the maximum for rolling out the cable is 1/3 of the wind speed, so it's slower than the wind speed. But the kite, as I said, flies much faster than the wind speed, and this is due to the lift. And so the second question to answer is how fast does the kite fly compared to the real wind? And so please look at the upper left side here. We have the real wind that's divided into the roll-out speed and the remaining wind, which I plot also here, which is 2/3 of the wind speed. The force that the plane experiences is, of course, always in line with the tether. That's the interesting thing, and I neglect gravity and also what we call cosine losses, so it's just assuming that the plane flies orthogonal to the wind now. There is an apparent wind coming from a slightly perturbed direction compared to the speed of the kite. And it's a well-known fact. Basically, it's like a gliding plane that's gliding in a vertical plane rather than a horizontal plane. The speed of the kite will be CL over CD times 2/3 of the wind speed, which is the remaining speed. This is the speed which brings the forces of lift and drag into equilibrium with the wind and with the force direction of the cable. So the force of lift is given by this well-known formula, half rho a v squared times CL. And then you plug this into the power formula again on the left bottom half, 1/3 of the wind speed, which was our roll-out speed, times this force. And for v, we plug in this number, and then we get Lloyd's formula. So it's a quite easy calculation, and you can see from this calculation also which simplifications we made in order to derive it. One can actually prove that this is an upper limit that any surface, any aerodynamic surface could harvest from any wind field. Yeah? And this formula has some implications which I don't want to share with you at the moment, but which are quite different from the usual considerations that you look at wind turbines. And one of them is if you maximize for the wind power per area, as we do here, you will dissipate actually 2/3 of the energy. So just to give an interesting bad number here. So it's just trying out to get the maximum out of a wing area. So, but what is this 40 kilowatt per square meter? 40 kilowatt is like the peak power at a good wind speed. Of course, there is capacity factors for all renewable energy systems, and we estimate that about 25% of the year this will run at full load. So we get on average 10 kilowatt per square meter of wing surface. But that means, here you have a picture of 2 master students at KU Leuven that are holding a wing of actually 1 square meter surface. The little plane is not necessary here. But this wing would be in principle enough to cover all their energy needs if it would fly all their life, of course, when there is wind. I want to compare this to solar energy. So this is like a race between solar energy until the end of the talk. Even though I'm a believer in photovoltaics, they really take a large area, and so you would need 250 square meter of photovoltaic cells here for the same output over the year. So because this is an exciting number, there is a community forming, and there are growingly people attending the conferences that we created, the Airborne Wind Energy Conference series. Here's one in Leuven. The next one will be in Delft this year. And some are in the US. We try to oscillate between the 2 continents. And if you look at these conferences and you talk to people, actually you can see that there are different concepts existing, and these ground-based and onboard generation, these 2 variants that I explained, they are not the only truth or the only division line, but there's also a big division line between fixed wings and soft wings. So for this ground-based pumping cycles, you have both fixed wings and soft wings. Soft wings look like parachutes or like kites, and fixed wings look like airplanes. And if you look at this onboard generation, we only have fixed wings. And the reason is that you need these very high speeds in order to make your generators light and efficient enough. So the soft wings are not efficient due to the low speed. They would just be too heavy, in particular the generators. So it would not fly. So these are the 3 concepts that serious people look at. There are some other non-crosswind systems in the domain of airborne wind energy, but I don't want to talk about them. So all these systems are actually built, usually in prototype form nowadays. The soft wings are maybe the largest that exist until now. And these are companies, startup companies usually. Only one in fixed wings with ground-based generation, and only one with fixed wings for onboard generation. These are very complex because of the fixed wings, which sometimes crash and produce damage, of course. And the soft wing community is much bigger, in particular in Europe. And leading, I would say, is the company SkySails in Hamburg. The companies in TIC I want to come back to at the end, because they have exciting products and exciting prototypes. And also interesting optimal control problems. As I said, I want to talk a bit about the dynamic models of airborne wind energy, and a reference for this is a book that we edited 1.5 years ago, which contains contributions by 35 actors in the field, and they describe their systems from an engineering perspective and also from the mathematical modeling perspective. Also the 3 companies I mentioned. And the perspective that we took is a differential algebraic equation modeling. So our approach is focusing on optimal control. And so the differential algebraic equation models for tethered airplanes that we look at, of course, these models are unstable because the systems are unstable. They are very nonlinear due to the aerodynamics and due to the fact that we have rotations and a flight pattern which is very different from a usual flight pattern for airplanes. So you can try to formulate these things with minimal coordinate models. Yeah? So taking just this like a robot with some links, which are non-actuated. But that gets incredibly complex very quickly. So if you print out the model equations, you get pages of equations. So we use minimal natural coordinates, or the rotationless formulation, as it's sometimes called, which leads to index 3 DAEs with invariance. And I want to give credit here to a team member, Sebastian Gros, who was a postdoc in my team and then moved to Chalmers University, who is now a professor for control of energy systems. And he supervised a lot our modeling activities here. And the reason why we are interested in these rotationless formulations is because it's much more flexible when we look at more interesting topologies. Like, for example, you might want to attach your plane to a rotating arm in order to start it up. And in order to model that, you get even more coordinates, and it's much easier if you formulate this as a plane, which is then bound together with an extra constraint to the arm. Also, I'm very interested, as you have seen from this introductory movie, in kites which circle around each other. And the reason I will explain in a minute. But let's first give an idea of how these differential algebraic equation models look like. And I wanted to illustrate it with the simplest example so that we all are on board what is happening in the background. So it's just one plane, as you see here, one tether which has a mass and a drag, but which is not modeled as elastic here. And we have an airfoil which is attached at the center of mass to this tether. So this makes the equations look much easier, but in reality, of course, it gets more complex. The inputs that we have are three. So the aileron allows you to roll the plane. The elevator, which is at the end of the plane, is allowing you to pitch, to change the angle of attack. And then we have, of course, the speed of the tether that can roll in and out. Actually, the acceleration of the tether is what we regard as a control. And then in the modeling approach, we will have 20 differential states, so 3 positions plus 3 velocities, 9 numbers to represent the rotation matrix, 3 to represent the rotational velocity, omega, and 1 length and 1 speed for the tether. And we also get 1 algebraic state in the simplest model, which is the force in the tether, basically. So the equations you see here at the bottom, the main equations, and as I said, there will be invariants, and these invariants are interesting for the sake of optimal control, so I want to state them once, and you are all familiar with this. You have the tether length constraint, you have its derivative, and we have the rotation matrix orthogonality. These invariants are actually automatically preserved by these equations, and if they are satisfied at one point on the trajectory, they will be, in theory, satisfied everywhere, but we need to impose them in the context of optimal control at some point for our equations to make sense. So, I wanted to outline these 2 non-trivial topologies. The first one is this rotation start. This is the device that you could imagine to start up such a plane. You would rotate it on an arm, and the vision is this is a computed orbit by Greg Horn, a PhD student of mine, where you actually bring it to speed and you rotate it faster and faster, and then you sling it into the power-generating orbit that you see here in big. Of course, this is an incredibly complicated maneuver. If you want to fly it, you wouldn't like to fly it with a pilot on board, but an autonomous plane might be able to do it. We are trying to simulate not only but also to do little experiments. And here you see a setup that we use in Leuven for working with these planes and experimenting with optimal control and modeling techniques. So here you get an illustration of how the system looks like. I will come back to this a bit later. So the second non-trivial topology, which I find very interesting and exciting, are the dual kite systems. And the reason for this, the real reason, is that if you have 2 that circle around each other, they will have significantly less tether drag, because these secondary tethers, they are the ones that drag, but they can be much shorter for a given height that you want to reach in the sky. So you can show, and that's what our simulations and optimization studies show, is that these 40 kilowatt per square meter is something you can reach with these things, also in the detailed models, with arbitrarily small devices, which is interesting because at the moment all the companies that are building one device, they scale up, and they try to scale up as fast as possible, because otherwise the tether drag will kill your system efficiency. So the tether drag gets relatively less important when you scale up the system, but for dual or even more kites, it would be significantly reduced and not matter at all for the size. Also, the centrifugal forces would compensate each other. So here's a simulation of such an airborne wind energy system. It's actually already the optimized size of, I think, a 25 megawatt system. A virtual one, of course. Here you see on the left the two dual kites circling around each other. That's how it would look like. And in the back you see sometimes at least a single bigger plane which would deliver a similar output. But it's further behind. It's actually much bigger. One thing I should mention here, I like this visualization because it shows also how these systems could look like. You would not see the tether in reality. This is not visible. It's much thinner. So to summarize the modeling, our procedure is standard and I think quite clean. You formulate the equations based on your best knowledge of physics, aerodynamics, and so on. Also, wind models need to be introduced, and so on. You use index reduction until the DAE is of index 1. That's our approach, so you can be flexible with your integrators. And then you formulate it, for example, in the semi-explicit form, which I state here, with a differential equation determining the derivatives of x, and the algebraic equations implicitly determining the algebraic variables z. So this is assumed to be of index 1 for all our studies. And what is important is that we also have design parameters p, which affect everything in our problem, and that are usually also open for optimization, together with the controls. And as I said, we will always have these invariants where the derivative is 0 by the DAE definition, and then we need to impose them at one time point on our horizon of interest. So this is on the modeling side, and as promised, I want now to talk about the numerical methods that we use for optimal control. So the second part of my talk is about the numerics. Let's first state the optimal control problem that we always address in this talk. This is an optimal control problem on a time horizon from 0 to t, which has an objective in this Boltzmann form, an integral and a Meyer term at the end. It has the differential equations and the algebraic equations as side conditions, also some path constraints, and all these three need to hold for every time point on our time horizon. And then there are boundary conditions which we state in this generic form, r of x0 and xt, and p needs to be 0, and they will be quite different for the different problems of interest. I want to stress that the initial value of our trajectory is not fixed, but implicitly it can be fixed by these boundary conditions. And actually there are three types of optimization problems that we really look at in this context and that are interesting and relevant for this talk. In the typical boundary conditions we look at first the periodic power optimal orbits. So that's a very intuitive optimal control problem. You actually impose that the initial state and the terminal state are equal, but you don't specify which value they have. They are free for optimization. You also impose the invariance at one point, for example x0, and then your optimization objective could very often be the maximization of the average power, and the power is actually tether force times roll-out speed, as discussed before, as your model equations give it to you. And note that the tether force is always positive, but it can be reduced by your pitch, basically. And the rollout speed is sometimes positive and sometimes negative when you have these pumping systems. And so the average power is really what you need to optimize, including some power losses during the real-in phase. A second class of optimization problems, of optimal control problems, arise in estimation. And here, actually, the initial value is completely free. The only thing is that we need to impose it somewhere on our horizon. We need to make sure that our invariants are 0. We usually impose it at the end of the horizon because we are usually most interested in the state at the end of the horizon in order to predict the future. And so that's why we impose it there for numerical reasons. The objective is then to fit measurement data y with model predictions, measurement outputs that your model would predict. And then, once you know the state, which you estimate with this moving horizon estimation approach, you can use it And you can actually impose this, which is a consistent state, as initial condition for your optimal control problem. So in the case of nonlinear model predictive control, which tries to look into the future, we have only this simple boundary condition: initial value is fixed. And the objective could be something of the form where we minimize a deviation from a reference that we would like to track with our states or some outputs. So these are the three types of boundary conditions we find interesting in this talk, as I said. And now the question is, how do we solve them? And here I like to look at the numerical methods for solving optimal control problems from a family perspective, where we have three big families which are competing with each other. The Hamilton-Jacobi-Bellman equation on the top left. But for us, the state spaces are too big, so this will suffer from the curse of dimensionality, so we cannot use it here. A second very elegant and used a lot in the space design questions of the 50s and 60s, the indirect methods based on Pointry against maximum principle. They have some difficulties with dealing with inequalities, which play a role in all our problems, so we will not use them either. And what remains are the so-called direct methods, which transform everything into a nonlinear programming problem, an NLP, which is then solved with state-of-the-art methods from another big community of applied mathematics, the nonlinear optimization community. But there are different ways in this family. There are three brothers: single shooting, collocation, and multiple shooting. And we exclude one of these brothers, single shooting, because it's only for stable systems, which our airborne wind energy systems are not. So we cannot use that method. And what remains is collocation and multiple shooting, and these are the two methods that we use all the time for all our optimal control problems that I will show in the following. I wanted to give a short note on this multiple shooting method that's due to Bock and Plitt about 25 years ago. No, 35. The basic idea is to discretize first the controls, like all direct methods, but then you solve relaxed DAEs on each of these discretization intervals, and you introduce artificial initial values, xi and zi. And by this reformulation, you end up with a nonlinear programming problem of this form. It's very structured, and it has very expensive functions phi I here, and a lot of science is going into how to make these solutions fast and efficient. So a few of the algorithmic developments that I can only sketch that are relevant and that have been done by PhD students or ex-PhD students in my group is some work by Joachim Ferraud, who is now at ABB, on an online active set strategy for QP Oasis. Actually, a remark: all our software is open source, so you can use it. Some of you might have used it already. Second big class of software is implemented in the Ecado toolkit. Its main or most exciting feature is that we auto-generate plain C nonlinear optimal control solvers that can then be deployed on embedded platforms, like even Arduino systems. Simple things, if we have small enough problems, I should say. And last, for more problems where the user is in the loop, so where there is still a human optimizing, we have the tool Casadi, which is an algorithmic differentiation and optimal control modeling environment developed by Joel Anderson. And some recent developments all in our team is Yannick Frasch, who did a joint PhD in Magdeburg and Leuven on a new band structure exploiting QP solver idea we had at some point during his PhD, which is very competitive and exciting. Rin Kirenen, who works on auto-generated implicit integrators, including the generation of these high-order derivatives. It's a very important ingredient of these algorithms. And on the other hand, Dimitris Kouzoupas, who works on fast QP solvers with a new approach called first-order methods. Or it's not a new, it's a very old approach, but it's getting very hot in the field of embedded optimization. So as some of the keywords I dropped might have indicated, our specialty is embedded optimization. So it's not only solving optimal control problems, but it's solving them on embedded platforms. Basically, it's optimization solvers which act on an incoming stream of data without human interaction. And so the most frequent paradigm that we use is you use sensor inputs like measurements of GPS, acceleration sensors, radar, and so on. You use these measurements in order to estimate your system state and to estimate parameters, We call this moving horizon estimation. You fit the model to data. You do this fast and quickly, maybe every 10 milliseconds, and then you use the state and you give it to the predictive controller, which is looking into the future and makes an optimal plan, and with this optimal plan realizes only the first step, like we do in real life, in order to send a command to the actuators. And these could be the flight surfaces, or for a car it's the steering wheel, joint torques for a robot. So it's a quite generic and very different control principle than classical control, but it's very powerful. And I want to illustrate what MPC is, this nonlinear model predictive control, by one example, which is the only example in this talk, which is not airborne wind energy. That's cars, because we all know cars. It's very illustrative to take cars. This is work by Robin Versturen, who is a PhD student with me and did this in his master's thesis with a company which got very excited with the setup, which was originally inspired by a team at ETH, but this is now experiments done in Leuven with nonlinear MPC. And so you have two cars, one controlled by Robin and the other with the predictive controller. The feedback is actually via a camera, so there's a camera on top that looks down to the cars. The task for you is to guess which of the cars is Robin's and which is the predictive controller. So, yeah. So Robin is not yet as trained as some really good car drivers, but the predictive control is doing its job fine. It's actually cutting corners, because that's really what it's designed for. It's predicting about 1 meter into the future, and this way it slows down before it goes into a curve, and it accelerates on long pieces. Yeah, it's recoverable. Yeah. Okay, so this is illustrating MPC. We also look at MPC for airborne wind energy systems, and because we are a small university team, we actually work with a small setup indoors where we can safely test things. So here we optimize with a sampling time of 20 milliseconds, leading to 50 Hertz re-optimization rates, and we use this Acado code generation. This is work by Milan Vukov, who just pre-defended his PhD successfully in Leuven. What we see here is on the right, actually just on the left, the sensors and the actuators. On the right, we see moving horizon estimation horizons. And this is actually the data assimilation problem. We are turning with the arm to make it more visible. And what you see is about 1 second in the past of our kites. The real kite is, of course, here on the left, but we don't look at it because you wouldn't see much. So at some point we switched on the controller, the predictive controller. It's actually doing its job very simply. It's just stabilizing to a reference here, because we cannot fly so exciting maneuvers here. But you can at least do something like going a bit higher or going down again, and you see that this controller is able to do it. The most important step for us was actually to make sure that all these communications work without the delays, that the numerics are fast enough. So we actually solve optimal control problems with DAEs of 27 states every 5 and 10 milliseconds for the MHE and MPC, respectively. Yes. But what we do at university is actually small compared to what is really happening in the industry. And that's why we also decided to team up with these companies and try to convince them that optimal control can play a role there. Actually, they sometimes even come to us. And as I said, I want to come to these 3 interesting, exciting companies, each representing one of the main areas for airborne wind energy. So let's start with MPX Power, the Dutch company. It's a startup from the TU Delft. It has 15 people. It's financed via venture capital. They are very innovative on financing strategies. You see their plane here, and they happily, we have 2 joint PhD students with them now. One of them is still open. And if you look at what they want to build, it's actually a pumping cycle to harvest wind power. So here you see it illustrated again. The plane flies a figure of 8, and then it's retracted when it has to retract. And if you plug this into an optimal control software, here we took a simple solution, collocation, IP-opt, Casadi for the derivatives. In an environment, you initialize it with a feasible trajectory, which is difficult enough to get. This is a feasible trajectory for the aerodynamic system. Usually this is already the result of a long homotopy process. But now we have this feasible trajectory, which is not pumping at all. It's not producing power. But then you start the optimizer. And the optimizer works and finds, goes down, so to say, finds a local minimum, which is close to Lloyd's limit. We can compare that, and which you don't see so much. It's actually just flying loops here, figure of 8 loops, and it's also rolling in and out the tether. It's an emergent phenomenon. We just gave the objective function, which is completely time invariant. But this is what comes out of optimization. And more interesting is maybe to look at the tether length. So here's the tether that goes longer and then at some point gets shorter again and ends where it starts. So the tether length, the optimal one, is also part of the optimization. And this is work of Giovanni Licitra at Ampix Power and Greg Horn, a PhD student with me. And interestingly, even with these detailed models, which have the drag of the tether, the mass, and the pitch and roll, and the interesting dynamics of the plane in them, and also wind model, we get about 1/3 of the wind speed. So it's confirming Lloyd's limit, and it's close to it, actually. Of course, much more exciting is what they do, and this is where all the work of the company is happening. They have this plane, and they started with a winch, like a sailplane. It goes quite quickly into heaven. Here we have not as bad weather as in Lecce, but bad Dutch weather, and that's the sky above the Netherlands. And now it's already going into crosswind flight, so you see it's flying an 8, so now it's turning. You see the sky, and at some point you see the ground on the other side, so now you feel a bit dizzy maybe, but there is no pilot on board, of course. And you fly an initial figure of 8. This, as I said, increases the force significantly, and here they start the retraction phase. So now they slow down the plane, and they just dive back towards the center, and now they go into the power production phase again, cycling a figure of 8. So it's a very exciting orbit. I should say it's not controlled with MPC yet. It's controlled with a sophisticated confidential controller of Ampix Power. So that was the first of the 3 startups. The second is SkySails. That's a company that exists since 2001. It's 30 people. It has traction kites for vessels, and since 2011 it's also interested in power generation, or they officially do it. It's financed by private investors and subsidies, and they have quite an exciting system, and I like to show this video, which has some sound, but that's not so important to show. Maybe I switch it even off. But they built a system that is pulling ships. These are kites of 300 square meter surface. They are pulling real ships, and they start automatically. The system doesn't take off economically for some reason, which is partly related to the price of oil, which is too cheap. But as I said, they also venture into power production. So here you have the generator, here you have their kite flying figures of 8, driving a drum, unrolling the cable, and producing power. And this is the vision that they have. That's not an experiment, that's just a vision. But they flew basically similar orbits like that one. And at some point they could land if there's no wind. And here you see the parks that we would imagine to have with these soft kites. There are some other companies. This is a company in Berlin that's doing a similar system, also pumping with automatic kites. Beautiful view here. And this is everything I wanted to show about that system. But we are in the happy position that the chief control engineer of SkySails is in close contact with us. He's now also getting on a joint basis doing some work with us. And And what he did, he flew in orbit already with his prototype, this one on the right here. And then he took the GPS data of that orbit, put it into the model. He has a very nice validated model for, which is also published for airborne wind energy. And then this is an orbit that he has actually flown to produce power. And then he puts it into the optimization tool, which he is a master of now. And then you start optimizing, and you compute. Here is actually the objective function that you want to maximize is shown here. It's a factor of the Lloyd limit, which is quite low in percent. But it's improving from 15% to 25% by just changing the form of this orbit in the optimization. And you might wonder why we are 25%, so very much lower than the limit of Lloyd. This is due to the slow retraction phase of these soft kites, which are not very easy to depower. So they actually go to the top to pull down, and then they move, producing power here again. The last company I wanted to introduce, and I think we started a bit late, but this will not take more than 5 minutes, is Makani Power. That's an American company. They do rigid wings with onboard generators. The company was founded in 2006. It has now about 40 people. And since 2013, it's part of Google X, so they got a quite substantial safety in their salaries now. This is the the CEO now of the company, Damon van der Linde. Very smart, very young American engineer with a degree in physics, bachelor degree in physics, MIT, and nothing else. But he's already leading this company at 27 years old. So here's the system they have built already. That's Wing 7. And if you look at what this wing is able to do, it's quite impressive. The beautiful thing is that they use their turbines that are on board in order to start and land. So actually, all of you know quadcopters. They are getting increasingly popular, not only by Amazon, but also by academic teams. And here, they use that to start. They hang, so to say, this setup into the air. It goes to the position where it can start power production. And at some point, they switch on, so to say, to the next mode. That is the power producing mode that's starting now. And from now on, the kite is driven by the wind, and the generators are actually acting as little wind turbines, 4 in this case, and they are flying circles in order to produce power. And they do this as long as there is wind, maybe hours, days, weeks, depending on the wind conditions and also the reliability of your system. But at some point you might decide to stop. Here they stop actually with good wind, I think. You just stop it, you hang it into the air. Now the generators are driving it like a helicopter again. It's flying and consuming energy. You're reeling in the cable slowly, steadily until it's landing. Here is a view from the bottom. And it's safely landed and you can rest and go home. So that's a system that they are now trying to scale up to a 750 kilowatt prototype. And while doing so, they work with us on the design optimization. And there's an interesting optimal control problem which I still wanted to share with you. That's a problem where we want to optimize the yearly power production of the system. And it's a multiple set point optimization because for every different wind speed, we will fly different orbits, of course. The only thing that we cannot change with different wind speeds is that the design parameters like the thickness of our tether or the length of the tether, and also the generator sizing and the airplane aerodynamic parameters. So the optimal control problem is a multiple set point problem where we have lots of discretization points for this wind histogram. They are weighted with their frequency. For each of them, we solve basically a periodic optimal control problem with periodic boundary conditions with the invariance. And the thetas are the design parameters which need to be the same for all of them. And so if you look at this from the optimization perspective, here's one of Greg's and Thomas. Thomas is actually from MPIX and Greg from from Freiburg. Here you see now the optimization. That's faster than it happens in real time. These are optimization iterations for all these different wind speeds, and each of them has an orbit, and you sum up, as I said, the yearly average power. There was no reference, so I cannot say how much it saved. It's just what they used to design their next plane. So there's one price question I still wanted to share with you. if you watched, I compared very often with solar energy. So the question is, when you would equip one of these Mercalli planes with solar cells on top, like these Solar Impulse famous plane that flew around the world. The question is, how much more average power would a Mercalli plane with solar cells on the wing deliver? So you can guess. So I heard the last one. It's the true answer, actually. So solar cells are not put on these planes for that reason. There's so much more energy in the concentrated wind power due to this crosswind motion. So to summarize, this single number that I would like you to remember, these 40 kilowatt per square meter wing area, which holds for the rigid wing prototypes. There is, of course, the message nonlinear optimal control can answer relevant design and control questions in this field. And also embedded optimization methods, they are tested on small-scale toy applications and they are ready for deployment on industrial hardware, hopefully also in the airborne wind energy industry. At the end, I wanted to recall what is our vision. So the idea is to replace tons of steel and concrete by a cable and optimal control. And there are 14 open PhD fellowships in this field. On the EVESCO project, they will be filled this year, but you can apply if you come from a different country from where the PhD will be granted. 2 of them are in Freiburg, in our control and optimization laboratory. Thank you very much.